Let's take a look at this example. A garage with no heating or cooling has a time constant of 2 hours. If the outside temperature varies as a sine wave, so we have our outside temperature m of t varying as a sine wave with a minimum of 50 degrees at 2 a.m. and a maximum of 80 degrees at 2 p.m., determine the times at which the building reaches its lowest temperature and its highest temperature, assuming the exponential term has died off. Okay, so we'll go back and revisit what we learned about this curve. So let's first, as we set t equal to 0 at 2 a.m., okay? And as you can see, we, of course, have this building, whoops, and that's the temperature at any time, and you can see that we have this temperature oscillating plus or minus 15 degrees. Now, how did we find that? As you can see, we have 80 degrees at 2 p.m., and that was our max. And then here we have 50 degrees at 2 a.m. So as you can see, m of t average is 65 degrees. And so it oscillates plus or minus 15 degrees above and below that 65 degrees. Okay, so we now are going to be able to write m of t is equal to 65 minus 15 multiplied by the cosine of pi t over 12. Of course, we find that since omega is the period of the cosine is 2 pi over 24 hours, and we come up with pi over 12 radians per hour. And of course, that's where we get this, because remember, this is omega t, okay? So now we have 65 as our average temperature. So we have 65 right here as our average temperature, and that is m naught. And then, of course, we have 15 degrees as our positive constant, which came from the oscillating temperature going between the average temperature and the max, and the average temperature and the minimum. Okay, so now we have the solution of our temperature equation. As T of t equal to 65 minus 15 multiplied by f of t, and we're going to talk about f of t in a moment, plus ce to the negative kt. Now, this is where f of t is equal to the cosine of omega t plus omega over k multiplied by the sine of omega t, all divided by 1 plus omega over k all squared. And we showed that that is equal to 1 plus omega over k squared. This is a nicer form, raised to the negative 1/2 power multiplied by the cosine of omega t minus alpha. Let me just move that. And we will use tangent of alpha is equal to omega over k. Okay? So, as stated in the question, we will assume the exponential term has died off. So now we have t of t is equal to, and we can also put t of t is equal to 65 minus 15 multiplied by, and I see an error here. I'm just going to fix this. (15) multiplied by f of t, since we are ignoring the ce to the negative kt, our exponential term. Okay, let's go ahead and plug f of t into this equation. So we have 65 minus 15, and we're going to use this form here. 1 plus omega over k squared, all to the negative 1/2 power, multiplied by the cosine of omega t minus alpha. So let's talk about this. Our temperature will reach a minimum when the cosine is equal to 1. So basically, we're taking the max value of the cosine function to find the minimum value of the temperature. Note, we take max value of cosine function to find minimum value of temperature. That's what we're doing here, okay? So that's equal to 1. The cosine is equal to 1 in order to find our minimum temperature. So we will go ahead and have t of t is equal to, is equal to 65 minus 15 multiplied by 1 plus omega over k squared raised to the negative 1/2 multiplied by 1. Okay, so that temperature minimum is equal to 65 minus 15 multiplied by 1 plus, and of course our omega divided by k is 2 pi over 12. All squared raised to the negative 1/2. And this, of course, comes from omega over k is omega times 1 over k. And omega was 2 pi over 24, and we had 1 over k was equal to 2. Okay, so 1 over k was equal to 2, and that was given to us here a time constant of 2 hours. We'll go ahead and write that. Okay. So, going ahead and solving that to find that minimum, we have that that's approximately equal to 51.7 degrees Fahrenheit. Okay, to find out what time that occurs, and we are going to set our equation. So we have 1 equals the cosine of pi times that minimum time divided by 12 minus the tan inverse of pi over 6. So we're using this here in order to come up with alpha. So alpha is equal to the tan inverse of W over K. And W over K is pi over 6. Okay, and so solving this, we will have cosine inverse of 1 is equal to, of course, that cosine inverse of 1 is just 0, is equal to pi t min over 12 minus tan inverse of pi over 6. So we have the tan inverse of pi over 6 is pi t over 12, and that minimum, that time where we have our minimum value of temperature is equal to 12 over pi multiplied by the tan inverse of pi over 6, and that's approximately 1.84 hours after 2 a.m. So approximately 3:50 a.m. Oops. Okay. So now let's go ahead and do what we did here. Note just gonna move some of this over. Okay, so note the cosine of omega t minus alpha equal to -1 will result in that temperature reaching a maximum. So we'll go ahead and do the same thing we did. So we have T of T is equal to 65 minus 15 times 1 plus 2 pi over 12 all squared raised to the -1/2 multiplied by a -1, and this is going to be our max. So we have T of T max is equal to 65 plus 15 times 1 plus 2 pi over 12 squared raised to the -1/2. And if you work this out, you get approximately 78.3 degrees Fahrenheit. Now, let's go ahead and find when this occurs. Oops. And we'll set that equal to -1, that cosine function. And this is going to be our max time minus tan inverse of pi over 6. And if you work this out, you'll get t is approximately 13.84 hours. And if you'll make note, it is exactly 12 hours later. So we have that it'll be approximately 3:50 p.m. when we reach that maximum temperature of 78.3 degrees Fahrenheit. Okay, let's look at this last example. Early Monday morning, the temperature in the lecture hall has fallen to 40 degrees Fahrenheit, the same as the temperature outside. At 7 a.m., the janitor turns on the furnace with the thermostat set at 70 degrees. So now we have U of t involved. So now we are including U of t in our equation, in our temperature equation. And when we are heating, our U of t is going to be positive. The time constant for the building is 1 over k is equal to 2 hours. And that for the building, along with its heating system, is equal to 1/2 hour. Assuming that the outside temperature remains constant, what will the temperature inside the lecture hall be at 8 a.m. and when will the temperature inside the hall reach 65 degrees? Let's go ahead and formulate U of t. We will go ahead and have U of t equals K sub U, and remember this is our positive proportionality constant multiplied by T sub D minus T of T. We also are reminded of our differential equation for the building temperature, plugging in our U of t. So dt, of course this is a function of time, equals k times m of t minus t of t plus h of t plus, here is our U of t, ku multiplied by T sub D minus T of T. Okay, so let's remind ourselves about what we were given. So we know that M of T is equal to 40 degrees, which is that temperature on the outside, and our hall is now that same temperature on the outside. We also have that H of T is given to be 0, since we do not have an additional heating rate. And we have that Ku is equal to K1 minus K, which is equal to 2 minus 1/2, which is equal to 1.5. We also have our desired temperature, is equal to 70 degrees, since that's the thermostat temperature. Okay, so let's go ahead and now write dt. Well, let me go ahead and go back into my other color. So now, therefore, we have dt is equal to 1/2, that's our k, multiplied by 40 minus t, that's our m of t, minus t of t, plus 1.5 multiplied by 70 minus t, that's this term, okay? So now we have dt is equal to 20 minus t over 2 plus 105 minus 3t over 2. And we have dt is equal to 125 minus 2t. We do have a linear equation here. So let's go ahead and write it in our linear form. dt plus 2t is equal to 125. Our integrating factor, we have mu of t is equal to e to the integral of 2 dt, which is just e to the 2t. We'll multiply both sides of that equation and have, let's go ahead and just jump right to that. We'll have the derivative, which is always our left-hand side, te to the 2t, equal to 125e to the 2t. And now, integrating both sides, we have te to the 2t equals the integral of 125 e to the 2t dt plus a constant. And going ahead and integrating, we come up with that. And then dividing both sides by e to the 2t, we come up with 62.5 plus ce to the negative 2t. Goodness. Okay, so now what do we have? This is our temperature at any time t. And now we will have, let's see, what color did I use? Pink. So we will have 7 a.m. We'll have t equal to 0. And let's go ahead and write that the other way. For t equal to 0, that is at 7 a.m. So now we're going to use t of 0 equal to 40 to find our constant. So we have 40 equals 62.5 plus ce to the 0. And so we have c is equal to negative 22.5. So we now have t of t equals 62.5 minus 22.5 e to the negative 2t. Let's go ahead and keep in mind that at t equal to 1, it was 8 a.m. And we can now find the temperature inside the lecture hall at 8 a.m. So now at 8 a.m., the temperature inside the lecture hall will be approximately 59.5 degrees Fahrenheit. Okay, let's make a few notes. Let's note. We note that the limit as t approaches infinity of t of t, which is the limit as t approaches infinity of 62.5 minus 22.5 e to the negative 2t, of course that term's going to go to 0, is equal to 62.5. Therefore, the temperature in the hall will never reach 65 degrees. And that was that last part of the question. When will the temperature inside the hall reach 65 degrees? It will never reach 65 degrees. And that concludes this video.